Got the recording started. So just as I said before, right, this is going to be just kind of going over some practice problems, preparing you guys for the final exam as much as possible. So the final exam is cumulative. Everything from exam 1, exam 2, and one extra topic, pushdowns. That's going to be what's on the exam. So everything back from Gödel numbers to regular expressions to context-free grammars to pumping lemma to Turing machines to all of that is going to be on the exam. And just to confirm again, if at this point you'll be able to kind of know what you got on like the second exam, and you'll be able to know your average in the class. So if you want to take the current average you have, if you're happy with it, if you get your C and that's all that you want, then you do not need to take the final exam. It is completely up to you. So if you have a lot of other exams going on, that's totally fine. Like you can prioritize those other exams. But if you want to try to get your average up a little bit, maybe you want to try to get into like a B range or an A range, then take the final. Use your own judgment. You can't do any worse. She drops below a score in that regard. So you don't have to worry about the final hurting you. It can't hurt you. If you have a C at this point, you can only go up. And if you're worried that you might not pass, if you're on the verge of passing, you can still pass. This final can still be your saving grace. So I just want to clear that up out of the way. Use your own judgment when it comes to it. There is no right or wrong answer of whether or not you should take the final. So use your own judgment. Okay, so we're going to get started with some of the questions. And if anyone has some of the old exams or old problems that you want to kind of cover specifically, perfect. Question we can
Sorry,
go over.
Lauren. Somebody posted that on the Discord, so I just pasted it here.
Oh, okay, perfect. That works. Yeah, so this is literally going to be whatever questions you guys want to go over. So if there's like a topic that's giving you a little bit more trouble, then like go for it, Okay, so let me get that up and running. So you should be able to see my screen. Great. Let me just pull up the problem itself and put it onto the whiteboard. Yeah, so the recording for this, by the way, it will be on the Learning Commons website. It usually takes a day or two to process just because it is kind of recorded to the cloud and it's a long recording, it's like a 2-hour session. But you are more than welcome to take a recording yourself if you want on your computer. On Mac, I know it's like Command-Shift-5. Windows, I think it's like Command-D or something like that. Whatever works for you guys, so go ahead. Also, if there's any point that you can't hear me, just let me know. So over here, right, we have ourselves a pumping lemma question, right? And this is one of those that we kind of have to decide, are we using pumping lemma or are we going to be constructing a state transition graph, right? So the key here is we want to really take a look at if there's links. That's the main thing, because state transition graph, right, an automata, it needs to be regular in order to do so. Right? If it's not regular, I can't draw an automaton. So we know regular expression and automatons, they go together. Now, I could create a context-free grammar from either of these, but not every context-free grammar can be made into a regular expression /automaton. Yeah, so we can totally go over that in the order of the topics from the class too. This was just something that was given in the chat, so we're just going to do this one first, and then we can definitely go through that order, as well as if there's any specific questions. So I could totally go over Gödel numbers after this. All right, so what is our language over here? We have three conditions. Firstly, the length of the string is equal to 2n for some n that exists in the set of natural numbers, right? That's what the capital N is referring to. Okay. The string contains exactly 1G. And none of the last rightmost n symbols is G. Okay. So if we think about this, right, this doesn't give us the links directly. We have to create them ourselves. So a lot of times people are confused. How do I approach a question like this? I don't see links. You got to create them yourself. We know that the length of the string is equal to 2n. So let me think of my very base case, right? If n equals 1, right, my length of the string is equal to 2. Okay, pretty simple, right? And if, let's say, my n was equal to 2 instead of 1, then it would be equal to 4. Now, I know none of the last rightmost n symbols is G. The string can only contain 1G. I can put the G anywhere, right? And I can make a regular expression or an automaton that puts a single G anywhere. That's easy. That's totally fine. What isn't so easy is this condition right here. None of the last rightmost n symbols is G. This is telling me that the rightmost n symbol, so if n is 2, the rightmost two symbols here have to be a non-G, right? It doesn't matter what it's telling me to do. It's telling me that in this case, I have to make sure that I keep track of the left and the right, right? We know that it's based on the number n, and that's going to essentially divide this into half. So I need to keep track of the left-hand side and the right-hand side of this. Because of that, I know that the left hand and the right hand are both going to be equal. This sounds like a link. There's going to be a certain amount of characters here, and they have to be the same number of characters here, right? Because of that, I can think of it as something like a to the n and a to the n, right? There has to be n characters on this left-hand side and n characters on this right-hand side. That tells me that I am going to be using pumping lemma. Okay, so because of this, right, I'm just going to go through the proof pretty quick on this, because with pumping lemma, it's kind of going through the template really and just kind of committing that to memory. Right. Usually this does take a while. So as someone said in the chat, you might want to prioritize that. Maybe you don't do pumping lemma first, unless you have the proof memorized. But I just want to make sure, you guys understand, like, okay, this is kind of how we get this sense of using pumping lemma from this. If it was not for this third condition, we wouldn't have links to deal with. Because we have links, we need pumping lemma. So we know that this automaton does not exist because our language is just not regular. And just as we said before, regular languages go hand in hand with automatons. To prove it, we need to create our characteristic property. The characteristic property is quite literally creating your links. Our links are saying that the symbol G does not occur in the right-hand side half of the string. And what that's saying is I split this in half, right? There's an equal number of characters to the left and to the right. Okay, so we assume that now L is regular, and we create our W0 using beta as our pumping constant. And this is going to simply look as follows, right? We know that there's going to be, in the example I gave, right, a to the n and a to the n. We know that there has to be a G somewhere in there, but the G has to be in the left-hand side, because I can't have a right-hand side having any G's, okay? Well, this is a bit of an issue, right? There's n characters plus 1 on this side, meaning I'm going to have to add 1 extra character to this side to make sure that they're both n plus 1 characters. That's where we get this W0 from. Okay? And we know that for this, the cardinality, its length is equal to 2 times L plus 1. Okay? We know the length is 2n, or 2L, whatever you'd like to use, plus that extra 1 for the G. And we know that the G can only be on the left-hand side. So now when we perform the pumping decomposition, right, of W0, this is essentially getting rid of anything in the sense that doesn't deal with our link, right? If there's anything that's not relevant to our link, we set its exponent equal to 0. So we only care about things that deal with the link. And that's all we're going to have here, right? We're going to just say that we're going to have x, y, z. So that's going to say x is going to refer to, okay, the pumping window y is contained within the prefix a to the L. So x and y are going to be on this side, and z is going to be on this side. Really what you're showing is that there's some arbitrary characters on the left, and there's going to be some arbitrary character on the right. And this is kind of like our generalized statement, right? Instead of actually creating something like what we had up here with actual letters from our sigma, we're just going to be using x, y, and z for that. Okay. We also know that the cardinality of y has to be less than our beta, which is our pumping constant, which has to be less than L, which is the exponent. Right? This makes sense because what we're proving is that our pumping window is too small. Because we're proving our pumping window is too small, right? We know that if we pump up twice from our pumping window, we're going to end up with the left-hand side pumping, but not the right-hand side. So that's how we're going to end up getting a to the L plus 2j, right? So we're going to, and then g, and then a to the L plus 1. So this a is going to get pumped up twice, and it's as if we're left with 2 a's. We're left with 2 a's, let's say, right? On this side, and a g. On this side, we only have 1a. This is showing now our link is not working. So we want to make sure that this doesn't happen, right? Because when we pumped up, even once it didn't work, but even if we did twice, right, that would result in 4 A's on this side and only 1 A on that side, right? This did not get pumped. This is what's within our window, right? This 1 A is what got pumped to become 4. Because this breaks a characteristic property, we know that this language cannot be regular. And that's exactly what this is saying here, right? The right-hand side of W1 amounts to L plus 1 plus J symbols, right? So literally, well, now the middle is all screwed up. So that's why we have a different ratio going on, right? Our middle is now over here, right? And look what's stuck on this side. There's a G on the right-hand side. This clearly breaks that characteristic property, right? That the symbol G does not occur in the right-hand side of the string. And because of that, we know that this is not regular, and I can't make an automaton out of that. And that's essentially how we do our proof. On the other hand, we can write a context-free grammar, which is what they have over here. But I think this one's kind of simple, so we can probably skip that part. But if you guys have any questions about this, let me know. Why can you write a grammar for it? Great question. So okay, regular expressions and automatons go hand in hand, right? I can write a grammar if something's regular. But if something's not regular, meaning it has links, right? Think about our simple example, a to the n, b to the 2n. This is quite literally saying for every a, have two b's. And there's going to be some recursive function in there, right? And if, let's say, I wanted this to loop, I could do something like that, right? And kind of just keep having it loop over and over and over again. And it's going to telescope outward, right? This is the same thing that's happening here. I'm able to essentially telescope outwards by saying that the length of the string is equal to 2n. So every time that I call s, right, I'm calling two letters on either side. That's where the z comes in. Then I also have to make sure that I have my g in there, right? My g is always going to be my recursive call. So this is going to let me have a recursive call here to just constantly add characters of 2 on either side to make sure it always has the 2n. And I have my g here and my t, which calls this over here, as well as z, right? So this is an extra character, making sure that for every one g, I have the one z. So this is essentially going to loop this as much as I want until I get up to this point here, which is where my mandatory g is. So I essentially can write a grammar for this. The only times I can't write a grammar for it is if there are links of 3 or intersecting links. So let's just go over what that's referring to really quickly, just so that we understand that, because that's also a very crucial pumping lemma point, right? We know that to prove that something is not regular, if it has any links, right? That part's nice and easy. Find a link, it's not regular. Do your pumping lemma proof. Now, if it's not context-free, right? We know context-free can have links. That's the whole point of having context-free grammars. I can't have links of 3 or more, and I can't have intersecting links. And what we mean by links of 3 or intersecting links is links of 3. Think about if you had something like this, right? A to the n, b to the 2n, and then g to the, I don't know, let's say n as well. Right, we know that we can pump this part. We know we can pump this part. We know we can even pump this part, the a and the g. I can only pump 2 things at a time. Because of that, if I pump the a and the g, right? The a and the g get pumped 1 time each. There becomes 2 a's and 2 g's. Who else gets pumped in here is the b, right? There's a b that gets stuck in there. And this b is not following it because now at this point, this b has its own ratio to keep, 2n. But because it was inside here, it was forced to pump once, right? Actually, no, it wouldn't be forced to pump at all because we're only able to pump these 2 guys, right? So because of that, I'd only have the original 2 B's. This guy doesn't get pumped at all. So this is saying for every one N, have 2 B's. Well, if we have 2 A's, I should have 4 B's. This is no good because this is saying I am not pumping this middle part. He gets stuck in the middle, essentially. Exactly, the property is broken. This is why we can't have links of 3. Now, what's an intersecting link? If I have something like a to the n, b to the m, c to the n, g to the m. And I'm going to actually have just 2m just to make this a little bit clearer, right? So we have a link here and we have a link here. Now, if I pump the A and the C, right? 1, 2, and 1, 2, right? Who is stuck inside? The B. This B is also going to be pumped, right? The problem is this is pumped against its will. There's a G out here who wasn't pumped. The pumping window is only this big. So that's why we can't have intersecting links. And any way you looked at it, right? If I pumped here, this B into this G, right? Who's stuck in the middle? The C. So intersecting links, you could think of kind of who's stuck in the middle. So these are the cases that would not be context-free. So if you have letters that look like this, like a telescoping grammar, then it's nice and easy to see this. Where it gets a little bit trickier is something like what we had over here, right? And for this, my advice is you got to just draw it out. You got to draw out the links yourself. For instance, for this one, I drew out my links. I knew that there had to be the same number of A's on the left and the right, or really any letter. I just used A as an arbitrary value. So I found that, realized it wasn't regular, and went from there. Maybe I would have found that there was a condition that made 3 different variables or broke something into thirds, right? Or maybe there was a palindrome involved. There's all different kinds of things, and it helps the most just to kind of draw it out into a example from that. So just because a language is not regular does not mean you cannot write a grammar for it. Wait, there are a little too many knots in there, but if a language is not regular, that doesn't always mean that it's going to be automatically context-free, right? Not regular doesn't just mean context-free. Context-free is not the opposite of regular. All context-free is saying are there links, right? Actually, no, if it's not regular, we know there's links involved. To be context-free, you can't break either of these properties, right? If you have links and they're not 3 or more and they're not intersecting, then they're context-free. So it's a little bit confusing at first, but that's the way that it works. Yeah, all regular languages are automatically context-free languages, but it's not the other way around. If we know it is regular, then we can write a context-free grammar. That's totally fine. But if we know that it's not regular, that doesn't mean we can always write a context-free grammar. So I think sometimes you could think of it as this, right? Regular is inside of context-free. Oh, not sure why that just happened. So all regular languages can be a context-free grammar as well, but not the other way around, right? There could be a little language over here who's in context-free, but not in regular. So you really got to check case by case. All right, a student has registered me to do this question. Yes, absolutely. I think this was from the exam. A lot of people had problems with this one. Okay, let's try this one out. Okay, everyone's favorite question, the baseball field question. I've done this one a few times, so yeah, I always think it looks like a baseball field. So this one over here is asking an important question. Is M a deterministic automaton? So I don't think we went over deterministic versus not deterministic in the last review session. So this is a bit of an important thing to go over, right? When you hear deterministic, right, you want to think of your path is predetermined, right? If you think about like history class, you probably learned about like predetermination, that your like future is already set in front of you, right? By like whatever deity or god there is, you know? So because of that predetermination, it works the same way here in the sense that your path is predetermined. So if I go over an example like this, right? I have one path, only one path, can only go that path. There's no way to go back and forth. There's no way to make an extra turn. There's no way for me to essentially get confused here, right? And even if I had something like this, right? Let's say B and then A, right? If my first character is an A, I go here and then I go here. If my first character is a B, I go here and then I go here. It's very, very specific. It's like there's a door for computer science majors and there's a door for non-computer science majors. Very, like very thought out, very simple. You know exactly what path you're going down. But what about if I had something like this? This is saying I have a lambda first. Starting out, what's forcing me to go down this path or this path versus just choosing the lambda, right? Lambda is like an empty string. I can choose anything. This is as if saying this is the path for computer science majors, this is the path for non-computer science majors, and this is for people who like pizza, right? Maybe you could be both. You're a computer science major who likes pizza. That's kind of us all, right? So what's stopping you from going down this path? Absolutely nothing. Your path is not determined. Fate is not here, right? You can make your own choice, your own free will. Well, what do we have here? Same thing, right? I can go down path C, or I could choose a lambda and just choose here, right? I kind of think of the lambda choice as you're kind of just taking a break, right? Instead of going here, you're just like, well, I'm done for the day. I'm going to check out and head to my finishing state. So this is why this case is not a deterministic automaton. So let's go through what her answer says. For instance, M has lambda arcs, say from T to Z. Okay, that's exactly what we have here, right? Lambda. Lambda can be anybody, right? It's non-deterministic. It's non-deterministic. And that's what makes it confusing, right? Now, on the other part is saying M also has non-deterministic choices, say from Q on B. Okay, when they say non-deterministic choices, notice how there's a path for B in a loop, but there's also a path for a B going here. Okay, if B was like, if you're a computer science student, this is saying, do I do the loop or do I go the straight path? You don't know. You have free will to choose. Your path is not determined for you. Because of this is another case that proves it is non-deterministic. And lastly, its transition function is not total. Say it misses all transitions from Z. So at this point, right, say it misses all transitions from Z. So you can essentially get kind of stuck within this automaton, right? In the sense that if I have just a single C, right, I could get stuck in state Q and never reach Z. I could also have the case in which I just choose a lambda, right? And I just result in an empty string. So this part I'm not too sure on, but I know for the other two parts, right? Lambda transitions like this are a big sign of a non-deterministic automaton. And also, right, seeing that you have two paths at the same point for the same letter. Those are the two main things I would keep in mind, right? She doesn't necessarily ask you to make a deterministic versus a non-deterministic automaton for most of the automaton questions, so you're pretty lucky on that. But, it's important to know this because if you're looking at this, right, you can kind of, you can have multiple paths. It's not just like a linear path that tells you exactly where to go. It's not like this part over here, right? Because we have this lambda, we don't know what direction we're going into. That's the main point that we want to keep in mind for saying whether something is or isn't deterministic. So I hope that that cleared it up a little bit. So if the starting point has multiple arrows, it's non-deterministic. No, yeah, exactly. Not specifically. If it has lambda or it misses arrows for some letters, right? Oh, okay. That's what it means by not total. Okay. So not total is saying there isn't a case for all letters. For instance, right? From T to Q, it can only handle a C or loop on a B. What if I want an A? Well, sorry, you don't have a way to transition at that point. So it's not totally able to handle everything. Okay. And before we tackle the next question that, oh wow, there's a couple of different sample questions to go over. Okay, we'll do those after. So usually lambdas in the beginning helps prove it's non-deterministic. Lambdas in general, right? How do you know whether to go down a lambda or not to go down a lambda, right? I can choose to go down a lambda here or go down A and B, right? There could be a lambda over here if I wanted to, and then, I don't know, C over here, or an A or whatever it is. This is also non-deterministic, right? How do I know that I want to go down a C or go down a lambda, right? I can just say veer off by having a lambda transition. And that's why we're saying it's non-deterministic, right? So it doesn't always mean that it's multiple paths, right? So multiple paths are honestly fine. It's just a lambda isn't necessarily saying that you have a string that looks like this, right? This is literally saying I have a string, and instead of going down this path, first I go down here, then I do this A. Then let's say I chose the lambda again. Then I went to another A. I can easily get this string AA by taking my two lambda transitions over there. And because of that, right, I'm starting with an A, you would think, oh, just take the A path. It's not very well defined in that regard. So it's as if you're saying, hey, you're a CS major, you should be going down path one, but you go down this path instead. Um, I think she'd give you full points for saying one component of why it's an NFA. I don't think you have to write this word from word, right? I mean, it's a the second you see that there's a lambda transition, um, or that there's non-deterministic choices, right? You know that it's non-deterministic, right? You don't need all three of them to make it non-deterministic. Just even having one is enough. So I'm gonna say that it would be okay. Yeah, exactly. There only needs to be one reason, right? Any of these reasons can be grounds for something being non-deterministic. So, all right. Before we move on to the next part, there is one last thing I wanted to go over. So some of these theorem questions, algorithm questions can be very confusing. This one is not that confusing. So I kind of want to go over how we're going to use Kleen's theorem in this, because this is like a question that might kind of come by a little bit more in the future. Some of these are just very confusing. I'll be quite honest, when I took the class, this was kind of done at the last few lectures, so I felt like I really wasn't prepared for this part. But for this one, it's honestly not too bad. And the reason is we're saying the input is an automaton and the output is a grammar. right? So this is an automaton to a grammar. Now we know all automatons must also be regular. Now we know I can create a grammar from a regular expression. We just had gone over that before, right? All regular expressions can be grammars. It just is not the other way around, right? I can't write every grammar to be a regular expression. This is exactly what we're proving here. We're going to use what's called Clean's theorem to prove pretty much exactly what I said. I can convert the automaton to a regular expression and a regular expression to a grammar. This is because, again, all automatons are regular. Regular expression can easily be converted to a grammar. That's all you got to really say. Now, if it was asking the opposite question, I think this is missing part B, which was the opposite. So let's go over that as well. If it was saying from a grammar, go to an automaton, right? This I can't do. I can't convert a grammar to a regular expression. This is not a given. Maybe the grammar is regular, maybe it's not. Maybe it's like the one we did before and there's links involved. I don't have enough information here. Because I can't convert this to a regular expression, I most certainly cannot convert it to an automaton. And once again, that is through Clean's theorem. That's it. If you happen to see a question that is converting between automatons and grammars, all that stuff, you want to make sure you're using Clean's theorem for a question like this. All right, let's take a look at what was posted in the chat. I'm not sure what Chomsky hierarchy is. If you have a question on it, but that doesn't sound like something we did. So I don't have the exam on me right now, so you'd have to just post a screenshot in the chat for any questions that you want to go over. Okay, so there was, yeah.
There was a part B to this question that I DM'd, I mean not DM, I messaged you on the chat.
Oh, okay, I think I see it. This one, right?
Yeah.
Great, okay. So this was the part B, I think, that I had kind of thought of before, or similar to it, I guess. Write a complete formal definition of a regular context-free grammar that generates L. If such a regular grammar does not exist, state that it does not exist and prove your claim. Okay, so all we're going to just do is just turn this into a grammar. Okay, and the most important thing to just kind of keep in mind is kind of where we're going on this, right? We know that our first transition from T, if I have a C, it brings me to Q. Otherwise, I can do a lambda and finish my whole grammar, right? So what I want to do is I want to say on my first state T, I want to say, well, I can do a lambda, I can do a C to bring me into state Q, or I could do a loop on a B. So that's going to look like T. I could do a B star, right? And we know that's just B looping on T. I can do C, which brings me to Q, and then a lambda. On Q, I can do a BC loop, right? So BQ, CQ, or I could do a G to bring me to X, or I could do a B to bring me to R. Okay. And because this is not a terminal or ending state, right? We don't know, we don't have the double target like we have in state Z. There's not going to be any terminal symbols, aka the lowercase letters. Okay. In state R, we know that we can loop an A or we can loop a C. Otherwise, we can also finish off with a single A. Right? This is just lowercase a, and it brings us to state Z, which is the end. Right? I don't have to say like A and then function Z. Z is the end. And then lastly, X is going to be, okay, I can do an A or a G to bring me to T. So A, T, G, T. I could do an A to bring me to R, or I could just do a lambda. And that would be the ends because that brings me to Z. And that's pretty much the end of the grammar, right? We want to make sure we write also the functions that we've used. Don't forget with your grammar, always say your veps, right? Your V is your variable. I guess you could say E, sigma looks like an E, is your lowercase letters. P is your production set. And you usually start with S. You don't have to. In this case, right, you're going to be starting with T. So it's vep T, I guess, for this case. And that's how we're going to do the grammar for this one. So the grammar was a little bit easier than the automaton itself. And honestly, it tends to be that way. Right? And this question here, D, explains to construct an algorithm that solves the following problem. Okay, context-free grammar to a regular expression. Just what I said here, right? I can go from regular to grammar, but I can't go from grammar to regular expression. When we talk about it generally, right? We can only do it if we know for a fact that it's regular, right? Then I know I can kind of convert between the two easily. But if I don't know what it is, generalizing it, I can't do that. Alrighty. All right, perfect. Yeah, definitely we can go over question 12. Okay, we got ourselves a Turing machine here. Okay, and there's a push down two that we could do after this too. Fantastic. All right, so Turing machine, right? We have ourselves our states over here. We start out at state Q, and our final state is W. So remember, there are two types of Turing machines. If there's a final state, you can accept on the final state, reject if you never reach the final state, or diverge on blanks to the right. If there is no final state given, you can either halt or diverge. So diverging meaning blanks to the right, halt meaning you never go blanks to the right. So we are going to find accept, rejects, diverge. Accept and diverge tend to be the easier ones. So a strategy to do on the exam is if you can't make it through all of the problems, or maybe the reject is a little harder, just focus on accept and diverge, right? You want to try to get as many points as you can. So over here, right, we're going to do L accepts first. So we want to get to W. Now this is asking that we want to do 8 distinct strings that belong to L accepts. But you know what we're going to do? We're going to do the regular expression too. It's good practice. And actually, we have to do it anyway. That's for part B. But the regular expression is quite literally the formula to get those strings. So once you get that, like, you're good. So kind of makes it a little easier for you. Okay, so we start out with Q, right? And for state Q, just gonna move that over. That way, a little bit of room to draw. So in state Q, I can go to state P on an A, B, or C. So if I draw out my tape here, right? I could do an A or B or C. And this is going to get me from Q to P. Now, if I have an A, I'm going to be writing a capital A. If I have a B, I'm going to write a capital E. And if I have a C, I'm going to write a capital K. This is important for when we go to the left, because we're going to have to see what we've already placed down. We also have a blank state here, but we're going to ignore the blank states for the time being. That's for the diverging later on. All right, great. Now in state P, right, I can do an A, a B, or a C to get me into state T. So from P to T, I could do yet another A or B or C. A, E, K. So I always know that I'm only going to have one character for each of these, right? A or B or C, A or B or C. Now that I'm in state T, I can do a loop. A, B, C, as many times as I want. A or B or C, star. Okay, this is just saying read an A, write an A. So nothing to really worry about with the writings. And this could be as many characters as I want, right? This is looping ourselves on T. So T, loop. When I'm finished with that, I am going to put a blank down, go to state S from the left. So I've said it before, but we have two types of blanks. Blanks to the right or diverge. A blank to the left, though, is like putting a period at the end of a sentence. A single blank, and now we change our direction. We go to the left. What are we looking at now? We're looking at the last character that we wrote. This last character has a choice to either come from the T star, if the star was greater than 0, or from over here, which was a definite character that we had to write. We know that we're going to have to look at state S now. So I'm going to be entering state S from the left. State S has one case. I must have an A. So I have to have an A from this. Well, I can only have an A from one place, from the star, because it's a lowercase a. If it was an uppercase letter, then it would have been fine to have come from either this or this. But again, we need a lowercase a. And if I had an A from here, it would have been a capital A because we wrote capital letters. Here, we're writing lowercase letters. So I know that I have to pop off one A from the star to bring me from state S to state X, right? And I'm going to continue going to the left. So right now, if I were to think about my string, right, we have A or B or C, A or B or C, A or B or C star, and my last character would be an A. That's where we're at right now. So we're going backwards. We're rewriting what we wrote already to be a little bit more specific. Exactly, there has to be an A because of that line. This line is saying, put a blank down, look at S from the left. Your leftmost character must be an A in order to proceed, right? And we're going to continue going to the left. Now that we're in state X, X has two possibilities. So X can either go on a B or an E. So regardless of if it's a B or an E, I know that I'm either going to be taking a B from the star or a B that writes to an E from this case. Regardless, I need a B. The B will either come from this or this. It doesn't matter because while I'm going to be going backwards and reading either a capital E or lowercase b, we know it comes from the same letter. So I know I'm going to need a B. Now, this will let me enter state Y. State Y is saying that I must have either a C or a K. Well, once again, right, I could either take a C from the star, which only reads and writes lowercase letters, or a K from reading a C from either of these guys. So I'm going to take a C. Now, after that, I'm in state W. And I know that I've reached my final state. So I'm all good. So I know that I can either do A or B or C, A or B or C, and then making sure that I have a C, B, A, right, at the end. I mean, I could even have A or B or C star there too. That's totally fine. Or I have to have a C, B, A just as my base case, right? The C can come from here, the B can come from here, and the A can come from here. That can work too. So if I'm going to simplify this, right, I can tell myself that I can do anything I want beforehand, which includes these two, right? I don't necessarily need them. All I really need is a C, a B, and an A, right? And I know this works because if I have a C as my CBA is my very base case, and I put this through the Turing machine, the C brings me from Q to P. Now in state P, the B brings me to state T. In T, I loop once and I do an A. I go backwards. In state S, I read an A. In state X, I read a B. In state Y, I read a K. I mean, a C, sorry. Which again, this would have written a K. This would have written an E. So whether or not I read CBA or a K and an E coming from this is totally fine. It's going to get me to my destination either way. So for this, I believe the string, yep, A or B or C star, anything I want in the beginning. It's totally fine to have anything else. And then CBA is my very base that I need. So when you say not simplifying it, you got to be a little bit more specific, right? If I left it as something like this, and then like this at the end, right? So let's just put this before it, right? If I just had like this, let's say, right? This is technically incorrect. This forces me to take two characters before that. So I do have to simplify it in that way. But if let's say there were like two cases that we found, if let's say that this B and this E, right, we know that the B and the E are coming from the same letter, B. It's just a matter of if we're at the beginning and we write an E, or if we're later on and we write a B. If it was two completely different things and we had to write two different paths and you didn't simplify that, that you can kind of work around. The most important thing is that you have all the good cases and none of the bad cases. This one that we had before, right? If we had included these two beforehand, it has some good cases, right? There's no bad cases, but the problem is we're missing a lot of good cases that don't have those. Like, what about CBA on its own? You might get partial credit for that, right? If we had A or B or C, A or B or C. But again, this is incorrect because you're missing out on a case that's literally just C, B, A. You have to go through it and see what is the smallest case that I can have to get myself to accept. And when going backwards, right, we know that we can take this C, we need a CBA regardless. But this C and this B can come from either the star part or from these two characters at the beginning. Because of that, right, these two characters at the beginning can simplify to just the C and the B. But in case they don't, we have the star. So that's kind of how we know we do got to simplify this. So when in doubt, still go for it, but be very careful with cases like that, right? Base cases, edge cases, from regular expressions how difficult it can be. So just be careful. Okay, someone got points for writing A or B or C before this. So that's, you might get points on it. Okay, let's continue with diverging, right? So diverging, right? First, let's say, where can we diverge? We can diverge in state Q or state P, and that's it. So because of that, right, in state Q, I know the second I write a letter, I immediately go to state P. Because of that, right, I need to have a part that would make sure that I don't go to the next state. That is lambda. An empty string can result in me diverging in state Q. Otherwise, as a second option, I can do the transition into state P, right? This would bring me from Q to P, but I can't do anything else. The second I have a second character in there, I'd go into state T, and state T does not have a diverging case. So my full answer for this is just going to be lambda or A or B or C. And that's it. Then, we kind of skipped over the strings. I think it's kind of self-explanatory. If you have the regular expression, you can make strings out of this. So it's kind of 3 points. The hard part is coming up with the regular expression, right? The easy part is literally using this. I can just have CBA with any character before it. Or in this case, right, I could have lambda, I could have A, I could have B, I could have C. Notice that there are not 8 strings that exist, right? That's a kind of a trick question here. So it can be impossible to list 8 strings, but write however many there are, right? Use the Turing machine and kind of just go through it if you're kind of doubting yourself with that. All right, then rejects, right? So for rejects, we want to think of kind of the opposite of what's going on, right? We know that if we have, okay, so, all right, this time she didn't give us the answer for that, but we can still do it. This might be a little bit of a tricky one, honestly. But for this, right, we know that we need to have a C, a B, and an A at the end. So anything that doesn't have a C, B, A at the end is going to immediately reject. So I can actually write in a couple of different cases, right? I could have A or B or C star. And then my last character is not an A, right? So if my last character is a B or C, does not matter what's before it, I'm immediately going to reject that. That can definitely be one case, right? I could have a case in which I have A or B or C star, whatever I want in the beginning. But let's say now I don't have, I can have, let's say if I have the A at the end, right? But I don't have a B over here, right? So A or C, right? This is totally fine, right? I mean, this is something that would reject. This can work. Lastly, right, there's C here as well. So I can do A or B or C star. Just don't want a C over here. So I could have A or B and then BA, right? Something like that, kind of forcing it so that each of these isn't there. And there's probably a way to simplify this quite literally. Yeah, it's the opposite of acceptance. It's everything that will not get you into accepting or diverging. Diverging is also important to keep in mind. So for this, right, we know that diverging has to be, you have to have more than one character. If you have one character exact, you diverge. So for this, as long as we have, right, actually, we'd have to have more characters here, right? This is saying if this star was 0, right, this is saying just a B or a C character. So I'm going to have to actually add a character in here to make sure that it ends up not diverging by accident, right? I don't care what's here. It really doesn't matter. All I care about is that there is a B or a C at the end. Because immediately that makes it reject. This would be okay because there's 2 characters, and this is okay because there's 3 characters. So this is probably not the most simplified way of doing it. And honestly, that's okay. But for this, like we know that we kind of hit the points for that, right? The advice for the answer, L rejects contains all strings of length 2 and exactly those strings of length 3 or more that do not end with substring CBA. Okay, so that's kind of like a more specific way of doing it, kind of what we have here, right? We quite literally formulated combinations that don't end with the substring CBA, right? Also to keep in mind, right, all strings of length 2, right? So I need at least 3 characters. So I could actually create a third case, which is literally just generalized A or B or C, A or B or C, legit just 2 characters. So in this case, we have literally everything that doesn't follow CBA. And then we just have a case that has 2 characters. So that's how we did that one. I think I don't think it would be honestly this long of a regular expression. This is like it literally just asking you 8 distinct strings that belong to L reject. And there's a reason for that because again, this is a lot going on here. So if you were to create, strings that follow this, right? That's the easy part. Just literally anything that doesn't end in CBA, and that works. Okay. And there's a question. Hello, can we go over context-free grammar and automatons? I sent an example in the general chat from exam 2. Do I still get some points if I don't name all the strings? So you only have to name 8, right? And I think you can kind of come up with 8 quite literally, right? If I was finding ones that just don't accept, right? I know that it has to follow CBA. If it's CB, it won't work. If it's CC, it won't work. If it's AB, it won't work. Anything of two won't work. If it's ABC, won't work. There's an infinite number of strings that you can do. So that's kind of the easy part. Okay. Um, a lot of stuff going on right now. Okay, there's requests for context-free and automatons. There's a push-down question. What do you guys want to go over next? Godels,
Totals, maybe?
push-down slash Godels. Yeah, absolutely. All right, two things for push-down. All right, if someone could find me a Godel question in the meantime. Rashawn, actually, do you want to take over for the push-downs, or do you want me to continue on that?
I'm just saying, like, if you need like a little break, I don't mind taking over.
Okay. It's up to you. Whatever you want to do.
No, 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 don't put me on the spot.
Oh, sorry.
No, 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 it's okay, it's okay. I'm just a little, if you like, you've been like talking for so long, do you want to like switch roles or or if you, it's up to you.
Yeah, it's up to you. I mean, I think we're gonna do a push down next. I just don't want to put you on the spot, for that if you don't want to.
I don't mind doing push downs.
Okay. All right. So I'll actually hand it over to you for a bit then.
Okay.
So I'll
But
stop
I'm
sharing.
not sure if the recording would stop if I start sharing or is that
Oh,
uh,
no, it's for the whole meeting. It
oh,
it'll keep going until like I stop it. So you're all good.
okay.
I know there were like two, I think, that you posted for the push downs. So whichever one that would work better.
Mhm. Sorry. So
Maybe going,
the
yeah, maybe going over the first one, I guess, the problem 670.
oh, okay, okay, yeah, yeah. That one I just kind of got it from the what do you call the problem book, but the other ones, somebody posted them in general chat on Discord.
Let me take a look. All right. Yeah, I mean, either is fine. I think the 670 is like kind of an easier example if we want to start off with that. Um, Otherwise, we could go straight into problem 11, which is pushed down as well.
I think we could do 670 and then the other exam. I mean the one from the exam.
Yeah, that sounds good.
Okay. So pushdowns are really similar to a Turing machine, like the way you read it. So Q is like the state, your starting state, and then this is what you read from the input. This is what you pop from the stack, and this is the state that you go to. And A is like the letter that you push onto the stack. So push down uses like a stack LIFO. So last in, first out. It's like that, like a kind of like a golf ball situation where you can get to the bottom unless you take out from the top. Um, I usually approach Turing machines and like push down questions with the automata. I'm not sure if there is a different way to represent pushdowns, but I do it with automata. So what I do is like sorry. create like the starting state, which is Q. And then from Q, I could reach T. And T is also my final state as it states in the problem that F is T. And I could reach T via A, where I pop off lambda from the stack, and then I push on uppercase A. And then from in T, state T, if I see a B, I can pop off a A and then push on lambda onto the stack. And then I go back to T, so that's a loop. Pop off A and then push on a lambda. Lambda is just nothing, so the stack would be empty if I'm not if I'm popping nothing off or I'm pushing nothing on. And then I could also see a C, and that I pop off a lambda, push on a lambda. So in my starting state, if I see a A, I have to pop that A off with the B later on. And I want to create a regular expression for that. So the first thing I would do is get from Q to the final state, which is T, is if I see a A, I go to T. And then in T, I need to pop that A off because the only way to accept in a pushdown automata is if my stack is empty and I'm in T, the final state, right? So what it looks like when I see I push on a A on the bottom. And then to pop that off, I need to see a B because B's I pop off A's and I push nothing onto the stack. So after I see this B right here, I could pop this off, this A off, and my stack would be empty and I would be in T. But the thing is that the C, we could see C's like in between A's and B's, right? And it doesn't really do anything. So we could kind of star that and then star the C's at the end too. I know it's a loop on B too, but the only reason I put one B and not B cleanly starred is because I only have one A, right? If I only have one A, that means that I could pop only one uppercase A off. So I could only see one B. Um, yeah. Lauren, is like my explanation okay?
Yeah, absolutely. So honestly, that's the best way to kind of keep in mind, right? Whatever you kind of push down, that's why it's called push down. You want to be able to see that to kind of pop it back up. And you want to end up with like an empty stack in the end. That's the goal. Kind of like you're putting down like a stack of pancakes, and you want to make sure that you get everybody's order. So everybody gets the pancake that they ordered in the order that the stack is.
I'm trying to find the other problem that somebody posted.
Okay.
Oh, got it.
Oh, okay.
Mhm. I'm trying to paste it on to this doc, but for some reason it's not pasting. Isn't it just copy and then paste it?
Yeah, usually I take a screenshot and like I try to drag and drop it.
if that might help a bit.
Oh, thank you. Okay, so where Q is Q and T, and then the alphabet is ABC, and then gamma, B, K, and Z. So this is not asking for a regular expression, it's asking for a context-free grammar. That's what kind of pushdowns are designed for. So for regular expressions, we have NFAs and DFAs. And to represent context-free grammars, we use the pushdowns because it has a little bit more memory than NFAs and DFAs, I believe. Um, so from state Q, let me make it a little bit smaller. From state Q, we could reach T. Via A, and then we pop off lambda and we push on ZKK. And then or we could push on ZBB. And then in T, we could loop on B's and C's. And if we see a lambda, we pop off a Q. Oh, sorry. Oh, okay, okay. The final state is Q. Okay, sorry. So if we see a B, uh, we pop off a B, uppercase B, and then we push on lambda. If we see a C, we pop off a K, and then we push on lambda. But if we see a lambda, we pop off a Z, and then we go to Q. And then we push on a lambda onto the stack. So it's asking for write a complete formal definition of a context-free grammar that generates L. So we would have our grammar equals V sigma production rule, and then S, the starting point. And we would have our S. We would have a S. We want to get from Q all the way to oh, I'm so sorry. For some reason, I thought this was a different state. So back to Q. I'm just gonna leave that there. Sorry. Um, so from Q, well, we're already at the initially we're at the final state, so that means that we can get to that final state with lambda moves. That's why we have a lambda there. Uh, or else we can go from Q to T and then go back to Q. So in T, if we see if we see a, then our stack would look like this. Z, K, K. Or it could look like this. Z, B, B. Right? There was two different ways you could push onto the stack. Is if you see a, you could push on ZKK or you could push on ZBB. Right? Um, so initially we have to push on these ZKK or ZBB, and let's say we push this thing on ZKK. So we will want to pop it off later on, starting from the K, right? Because it's LIFO, so we first have to take out the top part. The way to pop off a K is a C, right? If you see a C. So this K is off. Now we want to pop this K off again. The second K off. The way to do that is to see another C, right? And then your Z gets popped off with a lambda. If you see a lambda, you pop off a Z, so you don't see anything. It should be ACC for the KKZ place. And then now we have BBZ. That's the OR, right? So we first want to push it onto the stack by seeing a A, and then we want to pop off this B. Um, by seeing a lowercase b. We pop out of uppercase b. And then we want to pop off the second b by seeing another lowercase b. And that's you popping off two b's. Now you want to pop off the z, but the z is for free because if you see a lambda, you could just pop this z off and then go to the final state. Yeah, this. So this should be it because after this is just nothing. So that's going back to Q. Or you could recurse on this because of this kind of loop. So you're in state Q, you go back to state T if you see A. You could do this as however many times as you want. That's like SS. Um, Lauren, should I explain the algorithms too?
If you're able to, honestly, the algorithms are a little tricky, but if you do understand it, if you can explain it.
Um, um, I understand it, but it's a little bit, I don't want it to like, I don't know, explain it in a way it's like kind of weird. So can is it possible to like skip over these?
Yeah, definitely.
Okay.
I really wouldn't worry too much about those. Like the pushdowns themselves are kind of the best way to get points here.
I agree. Okay. You guys want to do the problem 12 or sorry, I haven't been paying attention on chat.
Yeah, you're good. Don't worry. I've been in the chat. We're good.
Okay, okay, okay.
We could do problem 12. Yeah, people are saying yes. Let's do problem 12, and then there's also one that was posted in the Discord as well. I'll send that in the chat after.
Okay. So let me get rid of the stuff for 11. Sorry. So problem 12 is similar to 11. You're just kind of pushing on different items onto the stack. It has similar states too, starting with Q. Yeah, Q is the starting state, and the final state is F, which is T. Um, you could loop on an A, and then you pop off nothing. You push on a ZK onto the stack. And then you could also push on a ZB onto the stack. And for free, you could go to state T. Okay. So this one has a different final state from the first one because the final state is actually T, not Q. And you could go to T for free, so lambda would still be one of the options because you see nothing, you pop off nothing, and you push nothing onto the stack. Your stack is empty, and you would still be able to end up on T. And then on T, if you see a B, you pop off a uppercase B, and you push on nothing. If you see a C, you push on a K, you pop off a K, and you push on nothing. Are you guys able to hear the pings on Discord?
Yeah, we can actually.
Okay.
I'll keep a watch on the Discord if anyone posts anything. So
Yeah, I'm sorry about that. I didn't notice. I didn't realize that the pings.
we still hear it actually. Is there another tab?
I think so. Give me a sec, please. Right. No, are you guys able to see, Lauren, are you able to see like my entire screen or just like the screen that I'm sharing right now?
So just your Google Chrome tab right now. So I just see the sketchpad.
Oh, okay, that's good. Um, the D, you pop up a uppercase Z and then you push on nothing. So from Q again, you could take you could take lambda to get to T and end up in the final state. So lambda would be part of one of the answers. The other way is that you could either take the A, you could loop on A, right? So if you see a A, your stack either looks like ZK or it could look like ZB. Now you take lambda steps and then you end up at T. In T, let's say you took this route, ZK. So you want to pop off this K first by seeing a C. So first of all, you saw a A, and then you want to pop it off by seeing a B. And that's gonna get rid of this K. Wait, I'm sorry. You pop it off by seeing a C. And then you wanna pop off the Z right here. So you wanna see a D. All right. The other case is you see a B and a Z. You see a ZB. I'm saying it the other way around just because stacks are LIFO, so last in, first out. Some instructions for T. All right. So to pop up this B, first you see the A, right? That's how you stack on a ZB. So you want to pop off this B first by seeing a lowercase b. And then you're like, okay, this is popped off. I want to pop off the Z by seeing a D. That's the other case. Um, and then you're like, okay, I ended up at T, but the thing is when I end up in the final state, I could recurse on this. So I could have as many like ACD, and then I could pick lambda, or I could do it again by picking ACD. Yeah. Lauren, would you want to take over for a bit?
Yeah, I gotcha. Okay. So there was another question that was also in the chat, so I will do that one. Also, to these people that are talking about Chomsky hierarchy and Dijkstra's algorithm, I think you're talking about the wrong class. Let me just get this question up. Yeah, I don't think that was from this class, actually. Okay, so someone had a question about telescoping grammars. And one second. Okay, perfect. So you should be able to see my screen now, and let's continue. So over here, right, we have a telescoping grammar. And so anytime that you have a regular expression like this, right, we know that this is definitely able to be converted to a context-free grammar. So with that being said, right, to convert this into grammar, what we're going to do is we're going to kind of break it down into different functions. And we can do that by saying anytime that we see a star, right? As well as usually anything that we see on the sides of unions as well. So we know that this entire regular expression here is separated into two pieces over here. This is the right, and this is the left. So I can separate these guys into two functions. We can say A and we can say B. So what we can do is we can do our starting point is equal to A, B, right? It's A or B. So we can either choose the left-hand side or the right-hand side of this. And on the left-hand side, right, we have the next part over here, which I'm going to do in another color. this part in parentheses is surrounded by a star. So anytime I see a star, I want to make that into its own variable. So we're going to make that into AD. Okay. And then from there, we're going to have another function as well. So we know that we can write inside the other star here. Wait, let's see. There's a star over here. And this star is for this parenthesis here. Okay, so this will be function E. So we know that A over here is composed of two outer functions, D and E. And we can go for D and E, right? Inside D, I know I can do the recursion because of the star. So I'm going to just handle the recursive case quickly by doing dd lambda. And then keep in mind the actual recursive case, right? I see that there's another star here, B star. So this I'm going to make into its own function f, right? Anytime I see a star. And this allows me to choose either a function fc or GA, and then concatenated with GBC. So let me actually write that a little bit different, right? I'm going to do A, the B star's function F, C, and this gets concatenated with GBC. Or I can do the second case, which would be GA concatenated with GBC. Right? So I don't have to create another function for that, right? I don't have to separate them because, again, it's not stars. So I don't have to worry too much about that. So I might be doing this a little different than the way she is. And if I am, that's honestly okay. The next part over here, right? D is completely done. We have E. So, right, actually, before we do E, F is very easy, right? F is just literally B star. So let's just do that. BF lambda. Again, I did the two different types of doing recursion here. Either is totally fine. You can do DD lambda, or you can do something like BF lambda. Either is totally fine. Just keep in mind, she'll probably use both on the answer keys. All right, now we can go on to E. So for E, right, I know that E is this entire thing surrounded by a star. So I'm going to start out by doing EE and a lambda, right? Just get my recursion out of the way. Now what's left? I could do B and then choose. Do I want GA or do I want to do B and then ACG? So I'm just going to say BGA or BACG. It's just literally choosing between these two, and there's a B concatenated at the beginning. All right, and now we're done with that part of the equation. So we're on the right-hand side with B, and once again, I see a star. I'm going to break this down into E, F, G. We don't want to use because that's grammar. Let's say H. Okay, so H is going to be CA star. So I have a star. Let me take care of my recursion first. H lambda, and then just simply CA. Okay, and then this gets concatenated with B or G, right? And this is going to be our entire case of B. So B is going to call function H, and then either B or G. So that means it's going to be either HB or HG. And this is going to be the end of our grammar. So again, I did this quite differently than she did, but as long as it gets to the point, it's totally fine. Yeah, you can create more functions. I This is just the way that I approached it. This is what made sense for me. You can make more functions than you need. I just didn't want to, honestly, and that's why I stopped at H. But you can absolutely do it. Like she had a J function, a K function. Like this K was literally just for this B or G part. She broke this down into a function. You don't have to do that because it's concatenated, right? That's the same as saying concatenating function H with B or H with G. Either is totally fine. So dd lambda will always be used for star. That's one way to do it. I could have done dd lambda, or I could have done, this was AF CGBCD, and then the other part GAGBCD, right? Just have and then a lambda. So having the recursive call at the end of each of my cases. I just found that it's a little bit easier to do that separately, right? Like handle my recursive call before I forget about it, and then handle the rest. This probably should have really been separated into its own function, honestly. But you know what? It's okay. It works. I believe she separated it, right? She did like a function D before GBC and then handled the recursive call separate. Again, it gets to the same answer, so it's totally fine. The most important thing to keep in mind, right? Stars and usually parentheses, but most importantly, stars. Those are going to need to be their own function. Right, so the second I see stars, I break it down into their own functions. Concatenation is totally fine on its own. Yeah, so you got a choice. You have less functions, but really long ones, or shorter functions, but a lot more of them. So you get to choose. So this is the grammar, and then for my V, right? What would I be using? S, A, D, F, E, H, B, right? So I did it with two less functions than she did. So can we do S to A, B, D, E? So A has D inside of it, right? A is this entire red line. B is that entire red line. So D is inside of that. Now, you could have split it up and said function D, then function E, then function H, and then B or G. That could have honestly worked. Um, but, sometimes it's a little easier to kind of break it down into halves like this, right? This is literally saying A or B. Yeah, it's everything in the parentheses. So this entire expression, S, right? S is the sentence, can be broken down into call function A, which is the left side, or call function B, which is the right side. Yeah, and all of that is inside of the parenthesis. I'll be honest, I think this might be kind of a mistake unless she did something completely different, because if she's saying that the string is entirely A and then B, this is a union, and the union is separating this part and this part. Unless my parentheses are wrong, but I believe this outer parenthesis matches with this outer parenthesis. So because of that, it's the entire thing. And you got the union there. If someone sees that, yeah, I'm pretty sure it's supposed to be A or B because this is saying A concatenate with B. And if it's concatenated with B, then you wouldn't have a union here. She's right. Okay. Unless she did something different than I did.
I do see the problem within her work because she's specifically making you choose in that order, where union you could choose like the first one and then the second one. So I believe it's also supposed to be A or B.
Okay. So function A is clearly this part over here, this left part that we identified, because we're saying that A is, or actually, wait. A is function G, it's function, sorry. A is composed of a recursive call of dgbc. So her function A is not including this function E, it seems, because it's saying I do a recursive call over this. That's what it seems to look like. Um, or actually, wait. Actually, no, I think I messed up a little bit because this is supposed to be a star over here. And I think the star is not for... Oh, wait, okay. This star is not for E. This star is for the entirety of A. Actually, is it? No, wait. This parenthesis matches with this parenthesis. This parenthesis matches with this parenthesis. Wait, no, hold on. Now I'm getting myself mixed up.
I think it's for only E.
This with this.
Oh no, is it?
Oh, wait a minute. This parenthesis goes with this parenthesis. So that means A is actually
Okay.
here, not here. Okay, you know what? Let's do this whole thing over again really quick. Okay, I'm just gonna move that over here. So this is the problem with these questions, right? It's very easy to mix up the parentheses on these guys. So let's just do this very quickly and then kind of go over that. Yeah, so I should just beat myself up for that, right? I mixed up the parentheses on that. All right. So this parenthesis matches with this parenthesis, meaning that concatenates with this. This is A. This is B. So that's why A is just AB. I mean, S is just AB, right? We're not doing the separation here with the union. If it was the union, then yes, she would be wrong. So we're going to once again have S goes to AB, right? Function A is going to be broken up into, well, first things first, right? We have a star around over here, right? And this is the entire function A. So I'm going to immediately do AA lambda. And then the inside of this, right, is going to be either A, another function for B. So we can call this A, B, C, D. Okay. So A, function D, C, or GA concatenate with GBC, right? So because this is concatenation, I'm just going to put GBC at the end of either one of these. So I can do A, all function D because of the star, C, and then GBC, or the second part, GA, GBC. This is the whole thing that's getting recursion. Okay, now we call function B. Or actually, while I'm at it quickly, D, we just know this is just B, D lambda. Okay, then for function B, right, now we just got to be careful with where these stars are. So this is a parenthesis. This, though, is a star. So this is going to be my function E. In fact, let me change the color of that. So this over here is going to be my function E. So function B calls function E, or, right, union, CA is in a star. So I'm going to, hold on 1 second. Okay. Sorry, I hope you guys going over. Decide to keep my windows open because it's a nice day, and yeah, perks of living by the airports, right? So okay, hopefully you don't hear it anymore. So now we have function E. Now this has a star as well, so this is going to be function F, and then it either is going to end with a B or a G. So this is going to be function E. You know what? I'm going to make this its own function too, because I'm just kind of over it at this point. So this is going to be E, or F concatenate with H, right? This is a function and this is a function. All right, now that we define that, E is just going to be, there's a star. So immediately I have my recursive case. And then I either choose B, GA, or B, ACG. Okay. Now for F, I'm going to have just simply CA, F, lambda. Again, I'm kind of just using both cases here interchangeably, and that's totally fine. H is just simply B or G. Okay, that is much better. Yeah, so that's why that kind of got thrown off a little bit. So just moral of the story, be very, very careful with your parentheses. This time I have S, A, B, D, E, F, and H. Okay. Do we need to go over the automaton too? Or do you guys have a different question to go over? No? Okay. Go over it a little bit. Okay. I'll go over it quickly. Right. So we know that we have a couple of different choices here, right? We know we're going to go to function A and then we're going to go to function B. Well, what is function A? Function A is saying I can do A, or I could do this A, B star C, or I could do GA. So this is going to be two paths, right? I'm going to do an A, B star, which is just a loop, and then C, or I could do G and then A. And then this is concatenated with G, B, C. This whole thing has a loop, right? And we can do this using a lambda transition, right? Just simply lambda going back and a lambda going forth. That's the end of function A. Now function B is a little bit different, right? We know that we're going to either choose a path that allows us to do function E, or the path to doing F and H. Now here's the problem though. E has a star. So because of that, if I had a lambda loop and it looped all the way back here, I could accidentally go down the second path. This is why Obrenic does a lambda transition to get us into one of these. You have to fully commit to path E or path F. So if I commit to path E, right, I can do, actually, wait, this would be path E. For some reason, it's on the bottom here, right? I can choose to do B and then GA or ACG. And again, this is a loop. I could go back and forth as many times as I want. But because I'm not going back here, I don't have to worry about accidentally taking the other path. That is the purpose of doing a lambda. So if you have different paths that have like loops to them, you want to make sure you have a lambda loop that essentially prevents you from going in the wrong direction. All right, and lastly, if we chose the F path instead, this is going to be CA loop followed by a B or a G, getting you to your final state. And that is the end. You don't have to have it going to exactly one state, one ending state. I could have had the ending state here and have another ending state over here. That's totally fine. Everyone draws it differently. And that is the end. Okay. Yeah, this is supposed to end like 3 minutes ago, but if you guys still have questions, I'll do a couple more. Do you need the last two lambdas? No, you do not. So these ones and these ones are only just because, for whatever reason, she wanted one final state only. There's no rule saying you have to have a final state. I could have had this be a final state and this be a final state and eliminated this part. It's fine either way. It just kind of matters, whether or not you want it to be, here you go again, deterministic or non-deterministic. And by the way, if anyone has to get going, there's a feedback form. Yeah, we connect them for aesthetics. Exactly. Yeah, if you guys could fill out the feedback form before heading out, yeah, don't worry if you can't stay the full time. We're going to probably just end in a little bit. I know someone had a question. This is on Gödel numbers, so let's definitely do the Gödel question. Okay, so this is the end of that one. Alrighty, let's do the Gödel. How likely is the recording to be posted before the test? What time? Sorry, what time? What day is your exam? Wednesday, right? I think tomorrow. Oh, the exam is tomorrow? Oh, okay. I will try to see if we could get it out as soon as possible. Um, yeah, if anybody happened to record it, um, please pass it on, I would have done it to my computer if that was the case. I probably should have really done that instead of doing a cloud recording. Sorry about that, guys, but oh, a few people were recording. Okay, amazing. Wonderful. Yeah, next time I probably will do it to my computer. I just get a little worried that like if I run out of storage, it'll stop recording or something. Yeah, my last recording of this ended up being like 12 gigabytes. My computer did not like me for that. Yeah, if it gets posted, if anyone recorded it, like post it in the Discord, upload it to like a Google link or something. I could upload it to YouTube as well. Godel will likely be on the exam. Everything has a fair chance of being on the exam. Okay. So anyway, let's do a Godel really quick, and then I think this will probably be the last. So, okay, Godel numbers, right? What's the important thing to keep in mind? Prime factorization, right? We know that this is a Gödel sequence that represents the following. This is the twos position, the threes, the fives, the sevens, and the 11s. So how do we get from a sequence, from a Gödel to a number? We add 1 to the power. So this is from a Gödel sequence to a number. So this is saying 2 to the 1 plus 1. 3 to the 0 plus 1, 5 to the 0 plus 1, 7 to the 0 plus 1, 11 to the 0 plus 1, right? So this becomes 2 to the second, that's 4, times 3 times 5 times 7 times 11. And this is equal to some number that we don't have the time to figure out at this point, but this is it. Right? She breaks it down into, I think, 20 times 21 times 11. Break it down into however works for you. And that's how you get this number. Now, if we had to go backwards, right? If we had to go from the number to a Gödel sequence, you subtract 1 from the power. So you take the prime factorization from this, right? We want it to go backwards, right? The way I would do this, honestly, is say this has 20 in it, right? I know that's equal to 5 and 4. 5 is a prime. That's great. Okay. And this is 20, right? And then, actually, you know what? Break it down into 10, right? This is like there's a 10 in it, right? I know 5, 2 is 10. And I know that this is going to be 462, right? These are primes, and this is just a number over here. I know that this is also, again, 2, right? You see there's going to be 2 2s here, right? And this is kind of easy to divide by 2 at least. 2, 3, 1, right? At this point, we're kind of not really sure, but kind of just continue as you go along. Sorry to cut this a little short, but you just kind of want to keep dividing on and on and on until you get to eventually. This is going to get you to, there's going to be a 3 here, there's going to be a 7 here, and there's going to be an 11 here. Right? And from there, right, you know that there's going to be 1 5, 2 2s, 1 3, 1 7, 1 11. So because of that, you subtract 1 from the power. So that's how we get 0 for the ones that we see once. So that's the 3, the 5, the 7, and the 11, and how we get 1 for the one we see twice, the 2. That's how we do Gödel numbers. All right, and this one is also a good one to do. So in case she gives something like this, if you have x1, x2, x3, x4, let k be the Gödel number, okay. Write a sequence of natural numbers whose Gödel number is equal to 34 times k and explain your answer briefly. Okay, all you want to do in this case is take the prime factorization of this number, right? If I'm saying 34 times k, that means it needs to follow both this and 34. So if it doesn't go into 34, that means I can't even do it in the first place. Okay, so if I were to divide this guy out, right? Divide by 2, right? And this would be 17, right? Its prime factorization is 2 and 17. But this is the problem, right? 2 and 17 means that this Gödel number would have to contain every consecutive prime. This Gödel number here only contains the primes 2, 3, 5, and 7. It's missing 11, right? 13, and 17. So if I were to say 34 times k, right, this number would follow 2, 3, 5, 7, and would follow 17, right? The 17 comes from this 34. There is no 11 and there's no 13, meaning I can't make a prime factorization out of it for a Gödel number. You can't skip primes. This one, though, I think will work, right? There's usually one that works and one that doesn't work. Write a sequence of natural numbers whose Gödel is divisible by these two, but not this one. Okay. This one, we want to take the prime factorization of each one, right? So 42. I'm just going to skip ahead and just say, we know this is 2, 3, and 7. Okay. 44 is going to be 4 and 11. And 39 is going to be 3 and 13. Okay. So that means that we need to have all of these powers, but not these two. So we know that if we're going to have a prime factorization of this, I guess a Gödel sequence of this, right? We're going to have 2 to the 1, 3 to the 1, 5 to the 1, right? Even though there's no prime here, right? Actually, this needs to be broken down. 4 is 2 and 2. Okay. Actually, let me go back 1 second, right? How many 2s do we need? We need 2. So this needs to be 2 squared, right? So I need 2s. I need 2 2s because 44 has 2 2s in it, right? That's the maximum number of 2s that I need. Okay, I need 1 3. I need 1 5, again, because it's a Gödel sequence. I need 1 7. I need 1 11. And at that point, I have all of them that I need, right? I have my 2, my 3, my 7, and my 11. I can't go past this point because the second I go to my next one, which is a 13, I lose the game. I have to have a 3. So even though I'm going to have a 3 because of this, right? I need a 3 here. As long as I never have that 13, I'm safe, right? That's essentially the game, right? You have 1/2 of the poison, but as long as you never have this 13, you're safe. So if we write this as a Gödel expression, it's going to look like this, right? And if we were just to take this into terms of x, right? This is literally just saying x1, which is some 0, right? You need to make sure you have one extra 1 to it, right? Because what is this Gödel expression saying? That I have x1, x2, x3, x4, x5. It guarantees that I have 2, 3, 5, 7, and 11. It's guaranteed I have one of them. Well, I need to guarantee I have 2 2s. Hence why I say x1 plus 1. The others are totally fine. I can leave x2 the way it is, x3 the way it is, x4 the way it is, x5 the way it is. I will not go to an x6 because what would an x6 mean? 13. What is 13? 1/2 of this 39. I have to have 3. I'm stuck with 3. Like that meme, right? I don't want you. I'm stuck with you. I have to have you, right? But I don't want you, right? It's like that up meme. Kind of losing it here. It's okay. So this would be our answer over here, right? We want to make sure that we have our x1 plus 1 for the 2, have x2, x3, x4, and x5, right? That represents our 3, 5, 7, and 11. And you shall not pass this. That's how we do that. So these are 3 possible Gödel questions you might see, right? This is literally, if you know how to do this, this is pretty much the only thing that I think, like the only ways that you can really format it at this point. It's going to be one of these essentially, either going from a Gödel sequence to a number or back and forth, or you're going to have something along these lines, right, where it says divisible by this and this, but not by this, or something in which it's multiplied by a number times k, which is literally just the Gödel sequence itself. So likewise, you want to make sure it is divisible by that number. That's Gödel sequence in a nutshell. Any other questions? 2 to the third. Great question. So this says 2 to the second, right? As long as I have 1, 2 in there, right? If I have 2 2s, it's guaranteed I have 1, 2, right? I need just the 1, 2 to make 42. So if I have a second 2, that's totally fine. I don't care if I have that second 2. 42 just needs 1, 2. 44, on the other hand, needs 2 2s. They borrow each other's. That's why it has a 3 in it, 7 in it, and 11 in it. Right? It's as if you're kind of multiplying them together, right? If you multiply 42 times 44 together, you know you're going to have all those 2s, all those, the 3, the 4, the 11, the 7, etc. Yeah, those are usually kind of easier questions. So if you can get these questions, this is an easy 10 points. And again, what do you need to pass? You need to, actually, for the final exam, you need some more points to pass. You need, I think, 60 points, but there's like 120 total. So it's more points available, even though you need more points. Yeah, I think you need like 60 out of the total 120 to pass. If you get 100 out of 120, this is like a perfect score. But this is doable because think about it. You're going to have like a wider variety of questions. If instead of 9 questions, maybe you're going to have like 13 questions, right? So even if there's like some that you can't answer, there's bound to be a couple more that you can answer. So use this as one of them. Finish that and do maybe like a regex, grammar, pushdown, maybe an easy Turing machine, accept and diverge, and you can get to those points pretty easily. Yeah, I mean, I'll be honest, the pumping lemma, it's a lot of writing, and she will not give you the template. She won't give you the template. So, um, it may not be worth it. Maybe it is. Maybe for you, maybe for one person it's easier. Everyone is different. Everyone has a different strategy. Personally, I think it might take a little longer. You want to just try to get through as many as possible. So pick your poison. Pick what's easiest for you. Um, so it's out of, I think, 120. It depends. Every exam is kind of different, but there's going to be more questions. So 60 points out of 120 is like a pass. 100 points out of 120 is like a perfect score. Honestly, aim to try to get to those 60 points. So if you can do 6 out of like 13 questions, that's like a little under half, then you're passing. So try to answer half the questions. If you can do that, then you should be okay. Stick to what you feel good about. You can do it. You got to do the questions. Just keep going, keep practicing. The more of these you do, the more you're going to be prepared. It's simple as that. So this recording is going to be on the Learning Commons website. I can actually post a link of that. Before you guys leave, though, please fill out the feedback form.